So let's try to implement a broadcast, a very simple broadcast. Right, so what is a broadcast? Everybody remembers what is a broadcast? We've discussed this, right? So some rank has data and that rank wants to pass that data to all the other ranks, right? As simple as that, that's a broadcast. So how would we implement that? Of course, you start with hash include mpi.h. Let me not write the whole program, but let me focus on the main components, right? So again, you have to call MPI init. For simplicity, right now, let's assume that there is a variable called buffer value. It's of type int. Let's say that rank 0 has this data, right? So it has b value, maybe it is equal to 100 on rank 0, okay? Numranks, rank. So first I need to get the total number of ranks. So I'm going to call MPI com size, right, with MPI com world and numranks, pointer to numranks. So this gets me the total number of ranks. And then I want to know what is my rank. So I call MPI com rank, again MPI com world, and into the variable rank. All right. Now let's say that if my rank is 0, right, then b value, the buffer, has a value of 100. Okay. Now what do I want to do? I want to basically send this value to all the other ranks. So let's write a simple code for that. Let's do something very simple, right? So every rank will just send it to the next rank. Okay, let's do that. So how do you write code for that? So rank 0 has to send to rank 1 will send to rank 2 will send to rank 3, and so on until it reaches num ranks minus 1. Yeah. So okay, the processing on rank 0 is different, the processing on num ranks minus 1 is different, the processing on all the other ranks is the same, right? So what does rank 0 have to do? Rank 0 has to just send the data to rank 1. What do all the ranks from 1 to num ranks minus 2 have to do? They all have to first receive the data. Once they receive the data, then they send it to the next processor, right? Next rank. Okay, and what does num ranks minus 1 do? It simply receives the data and that's it. End of story, right? Okay, so the code is conditional based on what is your rank, right? So let's do this. If rank is equal to 0, what am I going to do? I'm going to do a send, MPI send. So I'm just writing out all the parameters, right, for the first program that we're going to write, and eventually, subsequently, I'm going to skip a lot of this stuff, right? Hopefully it's obvious what we want to write. Okay, so what is the first parameter to MPI send? The buffer, pointer to the buffer where the value is. So ampersand b value, that's where the data is, that's where I've initialized the data. Okay. Second parameter is the count. So what is count? Well, it's a single element. What is the type of the element? MPI int, it's an integer. Destination, I can just write 1, right? So 0 wants to send to 1. Tag, I don't care, I just want to use a single tag, I'll just use tag 1. And what is the communicator? MPI com world. Okay, that's all rank 0 has to do, right? Rank 0 has sent the data. Okay. Else if rank is less than num ranks minus 1. Okay, so all the other ranks other than num ranks minus 1 all the way up to num ranks minus 2, what are they going to do? They have to first receive the data from the previous rank. So where are you going to receive it? Into b value. So it's clear, right, that this b value is different from the b value of rank 0, right? I hope that is clear, because each process has its own address space, right? So just because you're using the same variables does not mean it is in the physical memory it's the same variable, okay? Rank 0 has its own memory, rank 1 has its own memory, every rank has its own memory, right? So as far as rank 1 is concerned, the variable b value has not been initialized, right? All the processes are going to execute the same code, right? And this variable has not been initialized on rank 1. What happens on rank 1? It basically executes all these statements. It does not execute this if condition. It comes down, does not execute this if, and directly gets into this else if, right? All the ranks are executing exactly the same code, okay? And their memory is completely independent, separate, okay? Now, rank 1 is going to receive into its b value, into its buffer. And what are the parameters of MPI receive? Count, okay, in this case I know it's 1, it's not going to be more than 1. I am writing the code, right? So I know exactly how much I'm going to receive. If I was sending a string, maybe I would have set up some max value and so on, but in this case I know I'm passing a single integer, so I know I have to receive a single integer. Count, then type, which is MPI int, then source. I can't say 0 here, right? This code is executed by all the ranks. So I simply say rank minus 1. Whatever is my rank, I want to receive from rank minus 1, right? Here I could afford to write 1 because this was being executed only for rank 0. Small things, but it's important to realize these. What is the next parameter? Tag. So tag also I know it's 1, or I could say MPI any tag. Either ways it's fine. Then the communicator, which is going to be MPI com world. Right, and finally the status. So ampersand status. Okay, so I'm going to have to define another variable here, MPI status, a variable by the name of status, okay? And I pass the pointer to that. All right, so now I receive the data, and what do I do after receiving the data? What do these processes have to do? Pass it to the next rank, right? How do I do that? So again, that's similar to what I've already done for rank 0, right? Now my b value actually has the data, so I can send that data. One element of type MPI int, right? What rank do I want to send it to? Rank plus 1, right? Tag 1 MPI com world. Okay, so this is the code for all the other ranks except for the last rank. And now let me just quickly write the code for the last rank. So the last rank will simply post a receive. It just has to receive the data, right? 1 MPI int from whom? From rank minus 1, right? MPI com world and status. Okay, is this clear? All right, so this is probably a very simple way of doing a broadcast, but it's definitely not the most efficient, right? Particularly if you have a very large amount of data, right? What's happening over here? Rank 0 is sending to rank 1, which is then sending to rank 2, then to rank 3, and so on, right? Until it reaches the last rank, n minus 1, right? So if you look at these libraries, right, a lot of libraries are platform specific. If you look at any MPI implementation, given the underlying architecture of the interconnection network, they basically implement broadcast in a very efficient manner. They know the structure of the underlying network, so they do communication in a special way. But suppose that you don't know the underlying structures. Even then you can do something a little bit smarter than this. So what is another way of doing this? So what's the problem here? We discussed this also last time. So the total time it takes to send the data, if it takes to do one send and receive from one node to another node, if it takes time t, then what is the total time being spent over here? It is n minus 1 times t, right? Can we do better? Suppose we don't know the underlying architecture. So, okay, what does it mean by saying that I don't know the underlying architecture? So, typically when people say they don't know the underlying architecture, what they mean is that think of it as a clique, right? That's one way of looking at it. So, what can I do in this case? Is there anything else I can do which is slightly better? So, you could design all kinds of algorithms. One option is that rank 0 could just send data to all the processes individually, right? So, all these send and receive calls that we have discussed so far, right? These are blocking calls. What does that mean? What that means is that they don't return back to the user. The MPI send or MPI receive call does not return back to the user until the buffer has been freed up. Okay? Until this buffer that you have passed, until it has taken the data out of that buffer. What that means is that if you return from a blocking MPI send or blocking MPI receive, then you are free to use the buffer again. That's very important. Okay, so we'll talk about non-blocking calls tomorrow, but understand this, right? So one option is that you could have rank 0 send data to all the other processes, right, directly. But there are issues with that, right? The issue is that if you do it using blocking calls, so you post an MPI send, right, then you post an MPI send, then you post another MPI send. So rank 0 is posting MPI sends to all the processors, right? So this is sequentialized. This is sequential, so it's not scalable. If you have a million nodes, this is not going to scale, right? What are the limitations? First of all, it's making so many calls. Another issue is that this is getting into the internals a bit, but still important to understand that eventually when you send these messages, where do these messages go, right? So there are some network queues associated. So all this data has to pass through the network queues, the interface queues, right? The interconnection network queues, FIFOs, before it goes to the network, right? So this becomes a bottleneck. So this is not the best thing to do. I don't want to get into this right now. Okay, so this is basically quite simple. So what you do is, in the first iteration, what I'm going to do is 0 is going to send to 1. Okay, I mean we're just building a binary tree, that's all. Okay, so in the second iteration, what are we going to do? Well, 0 will send to 2 and 1 will send to 3. You're just doubling the work in every iteration, right? So in the first iteration, initially only one rank had the data. After the first iteration, 2 ranks have the data. After the next iteration, 4 ranks have the data, then 8 ranks and so on, right? That's the obvious way to do, just keep on doubling the reach, right? So in third iteration, what are you going to do? Well, 0 will send to 4, 1 will send to 5, 2 will send to 6, 3 will send to 7, and that's it. Yeah? Clear? Simple? Okay. How do we implement this now? So let's just quickly write a small MPI program to implement this. And as a matter of fact, just to let you know that when you go to a particular platform, there are MPI implementations which are specific to that platform, right? But then not everybody wants to design a new MPI library whenever they set up a new cluster, right? So there are generic MPI libraries available which do quite well in practice, no matter what the underlying architecture is, right? So there is OpenMPI, and then there is MPitch. So these are 2 libraries, right? And there are other such libraries also, which you can just download from the internet and start using. Okay. Of course, they are not tailored for your architecture. So these kind of libraries try to design the algorithms in a reasonable way, which doesn't work badly on most platforms. Okay, that's the way they try to design the algorithms for these MPI libraries. And this particular approach that we are discussing over here is used by these algorithms. It's called recursive doubling. This is used by these libraries quite often. Okay, it's a standard approach. It works for most collectors. All right, so let's just implement this. So what's the key over here? So let's look at two things, right? How do I know that I have to send data? Who is sending the data? So in the first iteration, rank 0 sends the data. In the second iteration, 0 and 1 send the data. In the third iteration, 0, 1, 2, 3 send the data, and so on. So in ith iteration, the first 2 to the power I minus 1 processes send the data. Okay. And whom does each node send the data to? So in the first iteration, 0 sends to 1. In the second iteration, 0 sends to 2. So in the first iteration, it's sending to plus 1. In the second iteration, it's sending to its rank number plus 2. In the third iteration, it's sending to its rank number plus 4. Right? That's the pattern. So what we are going to do is we are going to keep a value called counter, which is going to keep track of this doubling behavior, right? So it will be 1, 2, 4, and so on. So it is going to be 2 to the power I, where I is the iteration number. So again, I'm not writing the initial part and all, and I'm not giving all the declarations, right? We'll skip that part. Let's just come to the main algorithm. I'm going to run a loop. The loop is going to start from iteration 1, right? And what I'm going to do is I'm going to double the value of this counter in every iteration. Sorry. Okay. So basically this counter is 1 in the first iteration, 2, 4, and so on. It keeps on doubling. That's what I wanted to do. Whatever the counter value is, right, at the start of that iteration, all the ranks whose rank number is less than counter already have the data. Okay, do you see that? In the first iteration, counter value is 1 and rank 0 has the data. In the second iteration, counter value is 2 and ranks 0 and 1, whatever is less than the counter value, have the data. In iteration number 3, counter's value is 4 and 0, 1, 2, 3 have the data, right? Okay, so in the next iteration, counter value will be 8 and all the ranks from 0 to 7 have the data, right? Okay. So I'll put this termination condition later on. Let me just write the main loop right now. So what happens now is that if rank is less than counter, what does that mean? That means I have data. I have data to send. So I'm going to participate in forwarding this data. Okay. And who do I have to forward it to? If rank is less than counter, then I'm going to send my data. B value, again I have not given all the declarations and all, it's obvious what we're talking about. Again, whom do I have to send it to? Let me specify that, right? That's important. So whom do I have to send it to? Now this is the important part. I have to send it to rank plus counter. Okay? Is that clear? So just look at this, right? Counter is 1, 2, 4, 8 and so on. So when counter is 1, 0 sends to 1. When counter is 2, 0 sends to 2, 1 sends to 3. Another way of looking at it is if you're familiar with hypercubes, right? So what's happening? So this is the bit representation for 0. This is the bit representation for 1. So in the first iteration, what is happening is 0 is sending to 1. So wherever the first bit differs, right? In the second iteration, both of these have data, 0 and 1 have data. 0 is going to send it to the node which differs in the second bit, and 1 is going to send it to the node which differs in the second bit, right? So what differs in the second bit? So that's going to be node number 2, right? You see that, right? 0, 0, 0, 0, 0, change the second bit to 1, that's 0, 0, 1, 0, right? So it sends to 2. And 1 sends it to 3, because if you change the second bit of 1, it is going to become 0, 0, 1, 1. And in the next iteration, you can see, right, 0 will send to 4, right, because that's where the third bit differs, right. Then you're going to look at the third bit, so 0, 1, 0, 0, and so on, right. So you get the idea. So, okay, so all we are doing is, in any iteration, that's essentially we are multiplying by 2, that's nothing but shifting the bit left, right. So in every iteration, we are looking at the difference of the next bit and forwarding the data to that node. Okay, so there is something called the hypercube, right? This is the hypercubes. So there are algorithms based on hypercube. So this is node 0, 1, right, 2, 3, 4, 5, 6, 7. Right? So if you look at this, in the first iteration, 0 sends to 1. Right? So that's along the x dimension. In the second iteration, 0 sends to 2, 1 sends to 3. That's in the y dimension, right? And in the third iteration, just think of it as sending it down, right? They're all sending it down. So that's where they differ in the third bit. So again, we'll define hypercube more formally later on, okay? Basically, it's an arrangement where each node is connected to log n other nodes. And if you look at the identifier of these nodes, the ID or the rank of these nodes, they differ in exactly 1 bit, right? If you see the neighbors of 0, right, it's 1, 2, and 4. So 1 varies in the first bit, 2 varies in the second bit, 4 varies in the third bit, and so on, right? So that holds for all the nodes over here. Okay, let's come back to our program. So essentially, this is nothing but implementing an algorithm over a hypercube. Okay, let's come back. So what were we doing? So if rank is less than counter, that means I have data, I'm going to send it to rank plus counter, right, which is along the next dimension, right? Okay, and what else do I have to do? I have to receive the data also. I can't just be doing sends. There have to be receives in the code. Who's supposed to receive the data? If I am sending data to rank plus counter, then rank plus counter has to be receiving the data. Well, notice that all these ranks are those ranks whose value is less than 2 into counter. Because in the current iteration, there are counter nodes who have data, right? So they can only send it to another counter nodes, right? So all the nodes between counter and 2 times counter are going to receive the data, okay? So if rank is less than 2 into counter, then I receive the data. So receive into b value from rank minus counter. Is that clear? With respect to that rank, it's receiving data from counter ranks before, right? That's it. That's the code. Recursive doubling. Okay. Couple of things. First thing is, when do you stop? So what is the termination condition? Counter is the number of nodes who have the data. So while the number of nodes who have data is less than num ranks, you're fine. Yeah, so that's the termination condition. When counter exceeds num ranks, then everybody has the data. Okay? There's one bug in this program. What is that? Spot the bug. If counter is not a power of 2, right? So how do you fix that? Very simple. Just add here, do the MPI send only if rank plus counter is less than num ranks, right? Just put that extra condition in, okay? And this has to be a separate if condition. You can't combine this if condition with this if condition, right? You can figure out why. That's a simple observation. Okay, so that's recursive doubling for broadcast. Yeah, we started with some simple algorithms, but these algorithms are going to become more and more complicated as we go along. Okay, when we start looking at all reduce, when we start looking at topology specific algorithms, right, it's going to become more and more complicated. Okay, any questions?